Hello, welcome to everyone in this video. This is our lecture number 5. Already 4 lectures are covered. In the lecture 1, we start about the singularity point of a differential equation, right? In lecture 2, we discuss the Frobenius method, and then lecture 3, we discuss the special case of a Frobenius method, a special example. In lecture 4, we discuss about the legendary differential equation, its solution, legendary polynomial, recurrence relation, generating function, orthogonality, right? So if you want to watch the previous lecture, you can go through the description box, link are given there. Okay, in this lecture, that is lecture number 5, we want to discuss about the Bessel differential equation, right? Bessel differential equation, Bessel function of first kind, generating function, zeros of Bessel function, orthogonality. All about the Bessel function we want to discuss in this lecture, right? So let's start. This is the syllabus of the University of Calcutta for third semester physics honors. Mathematical methods. This portion actually covered in lecture 1, and in lecture 2 and 3 we cover up this one, and lecture 3 we cover a lot of portion, that is the legendary polynomial, recurrence relation, generating function, orthogonality, simply recurrence relation, expression of the legendary polynomial, write down, right? So all these things are covered in this lecture number 4. In this lecture, we want to cover this Bessel differential equation, Bessel function of first kind, generating function, simply recurrence relation, zeros of Bessel function, and orthogonality. Right? I think clear all about the root of our previous lecture and in this lecture. Right? So look at this. This is the total syllabus of mathematical methods of third semester of physics honors in University of Calcutta. So this is the differential equation, Bessel differential equation, which is like that. Like the legendary differential equation, this is a special type of differential equation which is occur in different physical phenomena frequently. That's why we solve these three cases, that is the legendary point differential equation, Bessel differential equation, and Hermite differential equation. These three differential equation actually frequently arises in the physical phenomena, different physical phenomena. That's why we want to solve these three cases in this Frobenius method. Okay. So this is the Bessel differential equation, and we can check the singularity point of this equation. You can easily find out the singularity point of this at the x equal to 0. You can say this is infinite, so this is singular point, and x into p of x equal to finite, and x square into q of x also finite. That's why this is the regular singular point. I think clear about the regular singular point if you attend the first class of this series of lecture. Since at x equal to 0 we got this regular singular point, so we can solve this differential equation by Frobenius method. That's why we take this series solution, because you know the Frobenius method. In the lecture 2 we discussed detail in the Frobenius method, right? So this is taken y equal to like that, derivative, first derivative and second derivative. Put this second derivative, first derivative in this differential equation, put this in differential equation and just rearranging them to separate out the coefficient of x to the power m plus k plus 2 and x to the power m plus k. Okay, now compare the coefficient of x to the power m. You can see here, if you want to find out x to the power m, here you need to put k equal to minus 2, which is not possible because k start from 0. But if you want to get x to the power m, here you can put k equal to 0. So if you put k equal to 0, you will get this equation from where you get the value of m equals to plus n and minus n, since a0 not equal to 0. Now if you compare the coefficient of x to the power m plus 1, you need to put k equal to minus 1 here, which is not possible, but you can put k equal to plus 1 here. You will be get this expression where we will get m equals to like that. Since a not equal to 0, that means m must be m or minus n. Since these are not equal to n or minus n, that's why a1 must be 0. I think clear why a1 must be 0. So we got this initial equation value of m. Now if we compare the coefficient of x to the power m plus k, you can see here x to the power m plus k will be found if k put as k minus 2. So that's why this is k minus 2 and this is ak. So you get the recurrence relation, that is ak equals to like that. In case of m equals to n, because we will be get the value of m as n and minus n. So in case of m equals to n, you will be get put this value of m equals to n, you will be get this equation and just rearranging then Now put k equals to k plus 2, you will be get these things because we increase this, because k start from 0, right? So if you put k equals to 0, you will be get this thing, k equal to 2, you will be get this thing, and so on. So you will be get the coefficient, even coefficient and odd coefficient will be 0. You know a1 equals to 0, that's mean a3, a5, a7, a9, all etc. odd coefficient must be 0. Now the solution will be like that, ak x to the power m plus k, sin m equals to n, and this even coefficient only exists, so the solution will be like that. Okay. Now comes into the legend, Bessel polynomial. If you take this a0 as this value, if you take this a0 as this value, you will be get, if you put this a0 at this value, you will be get, that is the expression of the Bessel function like that. Okay, if you rearrange it, this is gamma function. You all know this gamma function. Actually, in the later class we will be discuss this gamma function in details, but at this moment you can remember that gamma of n plus 1 is nothing but the n factorial. At this moment you can remember this one. Okay, in the upcoming lecture we will be discuss about the gamma function, beta function, etc. But at that moment you can remember this as this, like n factorial. You know the n factorial is nothing but n into n minus 1 into dot 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 3 to 1 dot dot multiplication. Okay, so I think clear about the Bessel function. This is actually the Bessel function which can be, arises from this, put this value, using it, using this value you will be get this solution y, which is nothing but the Bessel function. And take the another value of n, which is minus n, put this value, you will get this recurrence relation, and putting this value of k equal to 0 to 4, will be get this a2, a4, a6, and so on. So the and the odd combination must be 0, so the solution will be like that. And this, taking this a0 value, you will be get this equation. So the general solution will be like that. This is the j nx Bessel function, and this is the j of minus nx, the negative of Bessel function. Okay, so this is the solution of the Bessel's differential equation in terms of the Bessel function. Next, go to the generating function of Bessel differential equation. Like the, legendary polynomial, you know, take there is a generating function. Here also we take a generating function to simplify this, Bessel's polynomial, or you can say Bessel function. This is the generating function, that is, this n limit will be minus infinity to plus infinity j n x d to the power n. This is the Bessel function, and this is the exponential, which is function of x and t. You can take this as a y, no problem. I think in the legenda we will take x and y. Here we can take x and t, no problem. In the legendary polynomial you can also take x and t. Okay, that's no problem. This is the notation. So using this generating function, you can just expand these three things. You can see here, if you want to find out j0x, that is t to the power 0, this 1 into 1, this into that, this into that, so this will be the infinite series. Okay, in case of, legendary polynomial, you know p0x was 1, p1x was x, but in that case Bessel function, these are the infinite series each of polynomial. Okay, that's why this is called legendary polynomial. That's why this is called the, sorry, legendary function. Okay, this is an infinite series. And you can see this j0, j1, j2, j3 nature will be like that. Here the important notation will be that the at only j0 start from 1, otherwise all start from 0, and this will nature will be oscillating and the amplitude will be decaying. So this is a nothing but the damped harmonic oscillating, right? And these j0, j1, j2 are can be expressed in terms of sine and cosine, because exponential and sine cosine are related to each other. Okay, so I think you can remember these two things, because this is an infinite series, so we can express this as a sine and cosine function. Now comes into some recurrence relation for the Bessel differential equation, which is as important for our examination purpose. Okay, so first recurrence relation will be like that, x j n prime x, prime means derivative with respect to x, j n x minus x j n plus 1 x. Okay, So this can be proved by there is two method. One is from this Bessel's expression, and another one is from the generating function. Okay, so if there is a mentioned in your examination whether this take proved from the generating function, you must take this way, or you can easily you can take any method if there is not mentioned in this examination, right? So in this expression, this is the general expression of the Bessel function, and you can take this as a factorial. These are the same thing. I think you remember this gamma r plus 1 is nothing but r factorial, and this is the n plus r factorial. Okay, now if you differentiate with respect to x, you will be get j n x equals to just derivative of this thing, that is n plus r, and this is n plus r minus 1, and there is a derivative half. So if you multiply x in both sides, so this will becomes x by 2. That's why this is n plus 2r, and these are separate out n and 2r. Now this is nothing but the jnx. This portion is nothing but jnx, and this is can be written in this form. And if we take this because you can see here, uh, sorry, you can see here this r and r cancel out, so this will start from r minus 1 factorial. That's why r not equal to 0, it will start from 1. And if you substitute this s equals to r minus 1, this expression will be like that. So s equals to 0 to this one, so you can see here this is nothing but the j n plus 1 x. This s and r are the dummy index, there is no problem because this is varies from 0 to infinity. So this formula is derived from this Bessel function definition. This can also derived from the generating function. You know, this is the generating function for the Bessel Bessel's equation, Bessel's function, generating function of Bessel function. So if you take the partial derivative with respect to x and partial derivative with respect to t, after getting that you will be get multiply with the x into 1 and multiply with the t into 2 and then subtract. This operation will be done. You can easily find out this relation very easily. Okay, so I think you can do this solution easily. Just multiply x with that and multiply with this t with that, so this will be t and 1 plus t, and this as a common. You multiply with this x, this will becomes like that. If you multiply with this t, so this will be t to the n. After dating that, you will be just compare the power of t to the power n, coefficient of t to the power n. You can easily find out this expression. I think you can do this yourself. And the next formula, next recurrence relation is like that. You can see this is nearly same, but there is slight difference. This is j n x, and this is minus n j n plus 1 x, and this is the minus j n x and x j n minus 1 x. This also can be derived from this previous one method. Just follow up this expression. I do not explain each step. You can do these things, just follow up this step, you can easily find out this relation. And using generating function, do the same process, but there will be plus after adding these two operation, that is this partial derivative with respect to x and partial derivative with respect to t, and multiply with respect to x and multiply with respect to t, and then they add up, you will be get this relation. These two relation, that is formula 1 and 2, is the important formula, because using these two formula you can easily find out the others formula. Like that you can prove this relation just taking this sum of these two formula 1 and 2, you can easily find out this relation. And if you take subtract these two formula 1 and 2, you can get this fourth number formula, like that. Okay, and this formula also will be derived from formula 1, just taking the first derivative with respect to x, or formula 1. This is the formula 1, multiply these things, you will be get this expression, and this is nothing but that one, because if you just remember, that is the derivative of through product is derivative of first one, and first one is constant, second one, and this is the derivative of first one and product of second one. Okay, and the sixth formula also can be derived from the formula number 2. If you take the formula number 2 and multiply with this these things, and you can rearranging them with this formula, so this is the for sixth formula recurrence relation. Okay, And now comes into the point which is the zeros of Bessel function. Actually this is the nature of the Bessel function, and you can see this is the all starting from 0 and only j0 x exceptional case, and the damped and this amplitude will be reduces, that the damped harmonic motion will be represent like that, and this value of x for which sin x is 0 is like that. So zero of Bessel function do not occur regular interval. This is not occur in regular interval. This is depend on this interval, and this interval actually nearly to pi. This is not exact to pi, but this is nearly to pi. Next point is the orthogonality of Bessel function. This is the orthogonality of Bessel function where x j n x alpha x into j n x beta x equal to like that, where alpha beta are the roots of the j n x equals to 0. If you put this equals to 0, you will get the value of alpha beta. Then this property actually satisfy in case of the basis function. Okay, this is your homework, or you can say do yourself this solution, this proof you need to solve. I think you can do this very easily. If there is any problem to solve this question, you must comment in the comment box. Okay, so that's it for today. This is all about me, and this is my contact details. You can connect with me this Telegram channel, and this is my other platform, and this is my YouTube channel details. Go to this channel, you will get the different physics related video. Like this session, if you learn something from this session, share this video to your friends so that he or she also get benefit from this video. Subscribe this channel if you need this channel. Those already subscribed, thanks for subscription. Press the bell icon to get the notification of upcoming video. In the next class we will be discuss about the Hermite polynomial. So take care, we'll meet to the next video as soon as possible. Thank you.